All right, welcome back. Again, I'm Lane Martin. I'll be the chair for the session. So our first speaker this morning in this session is an invited talk. It's Jason Kawasaki from University of Wisconsin-Madison. And are you guys set up or ready to go or not? I'll dance in the meantime.
I think we can be ready.
I can sit next to you, it's fine. So Jason is going to tell us a little bit about some interesting new ferroelectric materials, looking at these hexagonal ABC intermetallics.
Yeah, so thank you. So I'll try to convince you that intermetallic compounds, although this concept sounds very strange, are a interesting enough compound to be studying for ferroelectric, specifically that they have this property, or might have this property, that they be hyperferroelectric. Also that some of these are polar metals. So I'll start out by reminding everyone what our general picture looks like. So we're most familiar with thinking about ferroelectrics based on transition metal oxides, right? So here's an example of barium titanate. Useful for many applications, but there are certainly some limitations. So examples are these materials generally you can't make too thin. So for normal proper ferroelectrics, you can thin them down. They compete with a depolarization field. So they can't have long-range polar order for, say, monolayer thick films. Other sort of challenges, perovskite ceramics are often very brittle, and there are very few examples of materials that are simultaneously ferromagnetic and ferroelectric. All right, so all of this motivates the study of new classes of materials. They may not necessarily be better in all regards than perovskite oxides, but at least we can start to learn something if we branch out to other material systems. So there was a nice prediction from David and Karen a number of years back that said, well, specifically looking at this depolarization field problem. And the idea was that, they predicted this new class of materials called hyperferroelectric. So these would be proper ferroelectrics that would be stable against the depolarization field. You could make them much thinner. And the key thing to look for would be this sort of unstable LO phonon. Okay? And this first paper was predicted in this specific class of materials that are these hexagonal ABC ferroelectric semiconductors. And what do these materials look like? Well, in general, they have composition ABC. You can think of them as having a BC sublattice that is wurtzite. You stuff that wurtzite with an A site cation. It's related, so the polarization is given by the buckling in these BC planes. It's related to a higher symmetry structure where the planes are flattened. So you can sort of think of this as a stuffed graphite structure and a stuffed wurtzite structure. The calculated barriers to switching are similarly small as BTO, and the calculated magnitudes of polarization are similarly large as BTO. Okay, so the specific predictor, so these have some interesting properties. These materials generally have smaller Born effective charges. They're much more covalent than ionic compared to perovskite oxides. Because of this hyperferroelectric property, there would be no critical thickness limit. Ideally, you'd have faster switching out of these sorts of compounds. Also, many of these compounds happen to be magnetic. So a lot of them have rare earth cations at the A site. So perhaps this is another general class of materials in which to look for ferromagnetic ferroelectrics. And finally, a lot of these materials are actually natively metallic, and some are predicted to be Weil and Dirac semimetals. So there's a lot one could look for in this particular class of materials. Okay. These materials, of course, have a number of challenges. So despite the fact that hyperferroelectricity in this class was predicted almost 60 years ago now, ferroelectric switching in these ABCs hasn't even been demonstrated yet. One of the biggest challenges is that many of the natively semiconducting compounds are actually composed of very volatile elements. So from a material synthesis perspective, especially from a thin film synthesis perspective, this gives you lots of challenges, right? I'm an MBE grower. I generally don't want to put lithium and zinc into my nice, clean 3,5 MB system, okay? So I generally want to avoid that at all cost. Another challenge is that although some were specifically predicted to be ferroelectric, many of these compounds are actually natively metallic. So what are we going to do about that? Okay, so for problem number one, my first solution, since I was starting out, I started my lab at Wisconsin 3 years ago. I wasn't about to put all these nasty lithium in my nice new MBE system, so I decided to use Daryl Schlom's MBE. So at the same time I was writing up these grants, he was starting up this Paradigm Materials Innovation Platform. And he's very happy to put basically any material under the sun inside his MBE. So we've been one of the first users, and we're using it specifically so that we can put lithium and zinc metal into an MBE system. Since then, we've been building up our own system, sort of secondary, where we can sort of put very volatile materials in. But most of the results today I'll talk about are materials grown out of this Paradigm facility. Okay, so our solution to the second challenge, that most materials are metallic, is simply to start from materials that are sort of semi-metals, narrow band overlaps, and try to induce structural distortions and see if we actually can open up a gap. So specifically, I'll talk about alloying at this A site, trying to change the size of this A site cation, see if we can enhance the buckling magnitude and open gaps that way. Okay, so I'll start out by talking about these hyperferroelectric candidates, the ones that are natively semiconducting. And here the story really is, even before we demonstrate switching, we have to just control the right phase, okay? So here's a cross-sectional TEM image of one of our samples. So the way we grow our samples, so one of the compounds we started looking at was lithium zinc antimony. So again, it's this compound right here. It's a stuffed wort-site structure. We grow them in the Paradigm system. We use elemental metals for antimony and zinc. And we use an alloy for lithium and tin. And the reason we do that is because the lithium-tin alloy is actually very air stable, or reasonably air stable compared to lithium metal. And because the lithium vapor pressure is orders of magnitude higher than tin, we can reasonably evaporate just lithium inside. Okay, so we grow these by molecular beam epitaxy. We've chosen gallium antimonide 111 because it's a reasonable lattice mismatch. It's a little bit less than 3%. Okay. Our sample structure looks like this. So typically, we'll take a gallium antimonide 111B surface. We'll grow a gallium antimonide buffer layer. Here's what the reed pattern looks like, so sharp and streaky patterns with a hint of a ring of spots, indicative of a reasonably smooth surface. And then we grow lithium zinc antimony on top. Near lattice match, this 12:1 reconstruction goes to a 1:1 reconstruction, indicating that we've grown something smooth and epitaxial. So let's figure out what we actually grew. Okay? So if you take this sort of sample, looks beautiful in the reed, you do X-ray diffraction, here's what you get. So these very sharp reflections, so this is a substrate reflection, this is a substrate reflection, this is the cap of zinc that we put on top. And in addition to that, we actually see two sets of reflections that correspond to the film. If you look a little bit more carefully, this actually corresponds to a hexagonal phase, and this corresponds to a cubic phase. And we can confirm that by cross-sectional TEM from our collaborators. So we see regions, this whole field of view is the film, it's lithium zinc antimony. We have cubic regions with ABC stacking. We have hexagonal regions with AB stacking, and cubic regions. Okay? So if we look a little bit more carefully, cubic actually is a competing polymorph with the desired hexagonal phase. So this nonpolar cubic actually, in the level of DFT, is actually the lower energy phase, but by not that much, by about 10 EV or 10 EV per atom, sorry, 10 MeV per atom. So pretty small compared to KT, especially at elevated growth temperatures. Okay, so it's pretty reasonable to expect that at moderately high growth temperatures, we're going to have a mix of both phases. So what we did simply is we said, okay, instead of this sort of moderate temperature growth at 190, we cool the growth down, we grow at 150. We can grow what looks in X-ray diffraction to be pure phase hexagonal. We can confirm that it's hexagonal in the cross-sectional TEM. And this time, it's the interface between lithium zinc antimony hexagonal phase and gallium antimonide. Interfaces are reasonably sharp, and we can see Cusick fringes in the X-ray diffraction pattern. Okay, so overall, these are the various phases that we do observe during MBE growth of these compounds. So as a function of growth temperature and lithium to antimony flux ratio, here's where we started with this mix of hexagonal cubic. We cooled down, grow at lower temperature, we can grow pure phase hexagonal. If you grow a little bit too lithium rich, you can actually precipitate out a cubic full Heusler phase that's lithium 2 zinc antimony. Lithium deficient, you can form this layered zinc antimony phase. Okay. You might ask exactly why we've stabilized this hexagonal phase, specifically at lower temperature. It's still not quite clear yet. Some calculations by Karen suggest that no matter what strain state, no matter what reasonable strain state, the cubic is actually the lower energy phase, but again, only by about 10 MeV per atom. Okay. And lithium composition, we changed the lithium composition, that relative stability doesn't change so much. So it really does seem to be driven by kinetics. Okay. So now let's measure some properties, see if we actually have a ferroelectric film. So I'll say the caveat right up front, we haven't yet demonstrated switching, that's still on the list. But where we've started is at least to make use of a new fancy detector that our collaborator has. So Paul Voiles has been developing a new detector that will let us do 4-dimensional STEM. So 4-dimensional in the sense that we can image both 2 spatial coordinates and 2 momentum coordinates. So the basic idea is this lets us map out electric fields, right? So you have this electric field. If there's an internal electric field, there will be some sort of momentum transfer on the measured beam. That'll be proportional to the electric field inside the sample. So just as a first test of this, what we've done is we've measured this mixed phase hexagonal and cubic lithium zinc antimony. So this is the image. This is the STEM image. This is sort of the momentum transfer. The color scale is proportional to the momentum transfer. We can convert that into electric field units if we know the thickness well enough. Okay? And what we see is that in sort of this cubic region where there's no unique polar axis, we sort of see a mix of positive and negative momentum transfers, right? But in this hexagonal region, we see a sort of a uniform direction of momentum transfer. So that's all well and good, what we expect. We can do a similar measurement on sort of a pure phase hexagonal region, and we see sort of monodirectional momentum transfers. We're still looking around. We still haven't seen any obvious evidence for a domain wall yet, but this is still very early stage. Okay, so for this first part, we've shown at least that we know how to control the phase purity of these samples by lowering the temperature and MBE growth. I'll say right up front, these are the first epitaxial films that have been ever grown of lithium zinc antimony. We can map out built-in electric fields, and the real question is whether we can actually demonstrate switching. So we've been doing a lot of work sort of building up this growth capability in our lab using a very small MBE system. We're going back to Paradigm actually later next month to see if we can grow clean enough films that we can actually try to switch in a capacitor or switch by PFM. I'll say one big challenge here is that because we've got lithium and zinc, and this is not an oxide, these materials are very air unstable. So I think this is going to be very challenging. Maybe we can get to here. I don't have a good sense of how large the leakage currents are going to be. So big caveats, but we're at least getting somewhere. Okay, second part. Now I'm going to talk about our secondary strategy, which is to take these compositions that are natively metallic and polar and ask the question if we can induce strong enough structural distortions to open up a gap. Okay. So the basic idea looks like this. So here's an example of lanthanum palladium antimony. So lanthanum is at the stuffing site. Palladium antimony makes this buckled wurtzite lattice. Okay. And natively it's a semi-metal with some overlap of about 1 eV. According to Karen's calculations, if you could somehow induce about 2.5 times buckling enhancement in this BC sublattice, you would expect to see gaps opening. So we're trying to see if we can actually do that. Okay, and to start with, what we'll do is we'll first just try to grow, we'll start out with just trying to grow these compounds, the natively metallic ones, in the sort of unstrained state. So we started out by choosing 2 compositions, lanthanum gold germanium, lanthanum platinum antimony. We chose them because they're natively metallic. They're not magnetic, so it's a little bit easier to think about. And we've chosen to grow these on sapphire substrates. So you can see they're sort of single crystalline at the level X-ray diffraction. They're reasonably flat surfaces by reflection, high energy electron diffraction. And they're singly oriented and have reasonably sharp rocking curves. Okay, so we can verify that we have the correct structure, and it's in fact the polar structure by cross-sectional TEM. So here's the lanthanum platinum antimony. These arrows are connecting. These arrows are sort of the center of mass for the antimony and platinum, right? So there's some sort of long range. Some long range structural polarization along the C-axis, as you'd expect. Same thing for lanthanum, gold, germanium. And by second harmonic generation measurements, we show that they actually are polar. Okay. One sort of nice feature of these compounds. There's been a lot of talk about polar metals recently. Sort of questions about why should polar metals exist. I think that's more or less been answered. I'll say there have been proposals that polar metals might actually be useful for applications like ferroelectric capacitors, where you make the top electrode a polar metal, and this can sort of help solve some of the critical thickness limitations. So this is based on some work by Jim Rondinelli. One problem is that if you think about most polar metals that have been studied so far, they're not terribly great conductors. These materials actually happen to be reasonably good conductors in comparison to most oxides. So we think that might be a reason for further study here, but that's not the original reason why we were interested in them. Okay, so the original reason why we're interested in these compounds was to ask, so stepping back, you can do 4D STEM on these compounds as well. And that's what we've done here. Okay, so here's the HADF STEM image. Here's the 4D STEM image where we're plotting sort of momentum transfer or apparent electric field in plane and apparent electric field out of plane. So this is the direction where there's the structural polarization. And we measure apparent magnitudes of electric field that are comparable to what we saw for the insulating lithium zinc antimony. I'm still not quite sure what to think of this. If you can really think of where this sort of apparent electric field is coming from, especially because this compound's a metal with carrier densities on the order of 10 to the 20, 10 to the 21. Maybe it's obvious to some of you. I'm not used to thinking about these sorts of systems. I'm natively just an intermetallics person. So I'm very interested to see if any of you have some insights of what this actually means, or maybe we're measuring what we're not thinking we're measuring. Okay. But in any case, yeah, this is an open question and very recent. All right, so what we actually want to do is we want to take these compounds and see if we can induce some sort of structural distortion to see if we can open up a gap, right? And again, our target is to try to hit this about 2.5 enhancement of the buckling magnitude. And one way we've decided to go about this is to start substituting on this A site cation. So our baseline compound is lanthanum, has a really, really large cation radius, but there's a well-known lanthanide contraction. So let's take an anion like gadolinium. If this is smaller, the basic idea is that the C-axis separation goes down. You have enhanced BC-BC layer interactions that should enhance the buckling. Okay, and that's indeed what we see. So we've grown a series of gadolinium-doped lanthanum platinum antimony. Okay. We've gone all the way from 0 to 1. In the cross-sectional TM, we do see a steady enhancement of the buckling. So from the pure phase lanthanum platinum antimony to about 95% doping, we've enhanced the buckling by about a factor of 2. Okay? And if you go too far, the stable phase for gadolinium platinum antimony is actually a cubic phase. So this has gone too far. But we've shown that you can actually enhance this buckling by quite a bit. Factor of 2, we were aiming for 2.5. Let's see if that was enough. Unfortunately, it was not enough. Okay, so we find that, so here's the lanthanum platinum antimony, this sort of baseline compound. As you increase the gadolinium doping, the resistivity goes up, curves get a little bit flatter. We see some onset of some sort of phase transition right here. We think it's an antiferromagnetic transition because we know gadolinium platinum antimony is antiferromagnetic. But unfortunately, throughout the entire range, all the samples were metallic. So perhaps not good enough there. Maybe we have a little bit more room if we push beyond 95% doping. We don't have that much room left. Okay, so that was simply going from here to here, just changing the size of this cation at the A site. As you make this smaller, you enhance the buckling. Another way to enhance the buckling might be to use, instead of steric effects, to use electronic effects. So all the compounds I talked about so far have 18 formal valence electrons per formula unit. Okay, this corresponds to completely filled D10 S2p6 shells. If you go to compounds that have 19 valence electrons per formula unit, you can do some electronic reconstruction, sort of a Pyros-like distortion that causes these BC layers to dimerize. And this BC dimerization could be another way of enhancing the buckling even more. So I'll say the caveat right away. If you go from this structure to this structure, this is the structure we originally wanted that's polar. This dimerized structure is nonpolar, right? So it's not going to be a ferroelectric, but at least we can just sort of prove the principle that maybe some electronic effect could give us this enhancement. Okay, so we've grown similarly structured compounds. If you take lanthanum gold germanium, you replace germanium with antimony, it has one more valence electron. So this now has our 19 valence electron system. We see now half-order reflections in the X-ray diffraction. Okay, this corresponds to a doubling of the unit cell along the C-axis. Okay, and from cross-sectional TM, we can show that yes, we actually do enhance this buckling magnitude by about a factor of 4 compared to these 18 electron compounds. But again, the structure is nonpolar. And to sort of prove to you that we think that really this is a sort of electronic or Pyros-like distortion, we did some photo emission spectroscopy measurements. So these are just angle integrated measurements. And we'll first look at the DFT calculations. So if you take this lithium, gallium, germanium type structure, so artificially impose the unbuckled structure, what you would find is this blue curve with a very sharp peak in the density of states right at the Fermi energy. If you allow it to relax into this structure at the level of DFT, what you would find is this sort of shaded red structure, shaded red density of states with a suppressed density of states at the Fermi energy, suggesting that it is some sort of electronic-driven reconstruction. And if we measure in photo emission, we basically get pretty good qualitative agreement with the density of states calculation. Okay, so this work is very preliminary, but I hope I've at least convinced you that these hexagonal intermetallics are an interesting enough set of compounds to study, in addition to all the great work on oxides, in that these are new compounds these are new polar compounds that both can perhaps host hyperferroelectricity and perhaps other compounds related to magnetism in topological states that are stabilized by polar structures. We've demonstrated the first MBE growth in this class of materials. We've done it with lithium zinc antimony, which was one of the proposed hyperelectrics. We've also done it with lanthanum gold germanium and lanthanum platinum antimony, which are these polar metals. I'll tell you the gadolinium doped versions are quite interesting. In magnetotransport, they actually show signatures of chiral anomaly in the magnetic resistance. So I think there's some interesting directions to go in for looking at these as wild semi-metals. I showed you that sort of despite our best efforts, it's really hard to open a band gap in this particular class of polar metals. But the upshot is that they do have higher conductivity. So if you think of a specific application where you really want something that's polar and metallic, maybe this is the class of materials to look at. And we have our work cut out for us in really showing whether we can grow films of insulating lithium zinc antimony that are good enough to switch. And also some challenges in interpretation of what we actually measure in 4D STEM. So this work is here if you're interested in more details. And with that, I'll thank my 2 graduate students, Dongshui Du and Patrick Strobin, who did all the work. Paul Voiles for a great TEM collaboration locally. Karen Rabe, Conor Genser, Cyrus Dreyer, and David for inspiring this work and getting us down this road into the ABCs. Of course, Daryl and Hanjong for providing the great growth facility for getting us started, and some collaborators at Argonne for photo emission measurements. And thanks for your attention.
All right, the talk is open for discussion.
I would like to comment your last point. What does it mean, polarization for a metal? And there is an interesting paper came out in 2015. They show that if you have a metal where inversion symmetry is broken, you may have an Hall effect to second order, non-linear Hall effect. And they claim this is a kind of way of distinguishing, let's say, defining something close to polarization, because you only have, if you have a metal with inversion breaking. Okay.
Okay.
So I'm curious if you saw if the polarization, the built-in polarization in any of these compounds changes as you change the thickness of your layer, if you've explored this at all.
So the thickness of the film itself, not the thickness of the TM specimen.
No, the thickness of the film, I mean.
The film, yeah. So we actually haven't done that yet. All of our films so far have been of order 50 to 100 nanometers. And we haven't looked at any other thickness.
So I was wondering, could you give a bit more detail of how your polar metal looks like? I mean, you are still building a tri-layer with the polar metal in the middle. I mean, the one for which you measure this mysterious...
So these are the two polar metals we talked about. The ones that we have the more detailed field maps are this compound. Okay, so, and your question is?
But so this is a thin film. I mean, what do you have at the bottom and at the top of the...
So at the bottom, so this layer is about 50 nanometers. At the bottom, we have sapphire substrate C-plane. At the top, we've capped it with a very thick layer of germanium to prevent oxidation.
I mean, this was, it goes in the direction of the following. I mean, some years ago, we did a study discussing the switchability of polar metals. And we showed from simulations that in a metal you can have, but in a bad metal, and quite thin, you can have a non-vanishing depolarizing field, because essentially you don't have enough free charges to screen the depolarizing field. And you still need to do this, even if your material is a metal, right?
Does that make sense at densities around 10 to the 21?
I mean, I think in your case you have a film that is way thicker than what we were considering. In your metal is a better metal, so it seems to me that here you should not have any depolarizing field inside. But this is something that you could, try to convince your theoretical collaborators to run a simulation of. We can talk later if you want. But
thank you.
Yeah.
Yeah, so I think this is a great example of, the materials by design paradigm. But I'm wondering, when you were looking with the doping of the gadolinium, that was really looking at it from experiment, right?
Yeah.
But why not do the calculation first as a of the band gap or whatever density of states as a function of the buckling and see what opens the gap?
The real reason is that we were interested in the magnetic part. So we wanted to do the gadolinium doping anyway.
Okay, but still, it seems like you could put in the buckling, even if you did, and just
so
see what
if
that opens a gap or not, and how much it requires. It seems like you could still do that, and if it never opens a gap, then you wouldn't need to do the experiment if you trust the theory. But
I have a small technical question. So the carrier concentration you're talking about is always around 10 to 21?
Yeah.
So what's the upper limit? How far can you go with that?
How high can we make the carrier
22?
concentration?
I mean, where's the breakdown?
It's not something we've tried. So by what means, I suppose?
Well, doping, I mean.
Doping.
Yeah.
So we haven't done anything. We've only done this isovalent substitution. I don't remember the full range of carrier concentrations, but I don't think it deviated so much from 20 to 21 with gadolinium doping. We haven't doped with anything that's not isovalent yet.
Any last questions for our speaker? Long Chen, last one.
Well, in terms of switching, this is just one comment. If you can make the polar metal to be also ferroelastic, maybe you can achieve non-180-degree switching using mechanical stream. But to achieve a 180-degree switching, which is really highly doubtful.
All right, let's thank our speaker one more time. Yeah, I don't know what happened. Are you on here too?
Yep.
Do you want to find? I don't know where your thing was at. I'll introduce you.